right. I think we are live. We are. All right. Today is the last day. Hopefully you're ready. I always am. I always start off very excited for these courses, and by the end of it, despite the fact that, like, of course, calm and collected, but like, no, man, it wears on me. Always ready for the break. Today's 4/30, 2025. We're in our last week of CSE598 here at ASU. And so we're talking about kernel exploitation because that's kind of cool. So, memes, a hardest module. This guy, so the kernel exploitation module and MicroArch are the two that people pretty much universally say are the hardest two modules. Which one is harder depends on the person. I think it's about 50-50. Do any of you disagree with what you've seen so far?
So far, Kernel's a bit easier than MicroArch.
Kernel's easier than MicroArch.
So far.
Okay, no, that's fair. It's a different kind of hard, right? MicroArch, you can't debug, and so you're writing all this C code and you're not sure what's going on, and you're waiting for the CPU to get stuff. All right, maybe it works, maybe it doesn't. So it's hard to reason about what's going on when you're understanding the concepts. But MicroArch, especially since at least this semester, I've stressed libslub more than I have in the past. You have the ability to look at what's going on, and I think that helps quite a bit. The problem is, which I lie to myself about so much. I have so much about pwn.college. I'm just an optimist, right? I told myself all the way back in 466 I was going to fix this hardware-related thing when it came to VMs. If you remember, I still have it, and we're like 2 semesters later. We're like 80% of the way there, 90% of the way there, right? It's the last 10% that is always the most difficult. Hello, Twitch. Yes, your cute meme made it. It's a good meme. Right? It doesn't necessarily fit topically, but it's a great meme. And I'm a big believer in memes. Course grade. I haven't talked about this in a while, but it hasn't really been relevant, I guess. Everyone kind of has plugged along at a decent pace. I looked at the grades a little bit earlier today. This is including like right now, if nobody were to solve anything, right? As far as I'm aware, it's including extra credit. Grades page has the extra credit, right? I threw it on there at the beginning of the semester and didn't think about it again. So this has memes and yeah. Okay. So yeah, this is the class average across you guys. Honestly, I think it's great. Typically, that is what we see in this course. Interesting this time. There's nobody that is currently over 100%. I was there. I was surprised, given all the extra credit. Like, I'm told that people just do this extra credit and then just blow past it. No one's over 100 right now. But everyone's doing well, I think, given the roughly 2 weeks that are left in the semester. If anyone wants to go above this and get the A, I think it's only time to do it, regardless of whether you're tackling the kernel exploitation stuff or any of the older challenges. Oh, hopefully you guys agree. I don't think I yelled and screamed about it, but I try not to curve. I'm not curving. Oh, yeah. I know, big surprise. So this is the last stream of 598. I will do office hours this week as planned. I will try and do which I'll announce next week, a like proxy Discord stream for class. We don't own this room, so I can't say, hey, we're going to have class on finals week, but I will do a pseudo office hours around class time as well. So that way, if there is something, and it doesn't matter whether it's kernel or anything else in the course, if there's something you want to discuss, I'll try and make myself available, both for a pseudo class and for an office hours, with the both games. So we covered a bunch of stuff in this course. Hopefully you found it interesting, right? Even the Windows stuff, which is very different. It's very strange. It's a weird type of challenge setup. I think it's fun, right? To try and like come up with these very different type of challenges. Maybe they work, maybe they don't. But you put up with the live demo insanity, including whatever happens today, and we're on the other side of it, right? Like I think everyone is gonna pass the course, so it's good. Well, like with a class average like that, I'm pretty sure we are. So we're on the other side of it. Hopefully, you guys feel good. But does this mean that hey, I got my 598 grade here? I know everything, right? Is this really the end? No, it's not, right? This is really kind of the beginning of understanding these more complicated cybersecurity concepts. Right? We may have talked about format strings, and we talked about the heap, and we talked about Windows. We're really looking at these weird machines or this specific functionality inside of the computer, and trying to reason about, well, how does it work? What is something that's vulnerable? How could this be abused, misused? Let's think about this as, I believe Jan called it, a weird machine, right? Which is not just a Jan term, that's a legitimate cybersecurity terminology, right? And so you think about all of these subsystems or components or functionality in a very different way. And so that hopefully the skill that you learned here isn't, I memorized how to do a format string, right? Or I memorized how to do House of Spirit, right? Like, is that important? Maybe, right? The more important skill is the meta skill that you've heard me rant about for probably a year now, of using GDB and thinking abstractly, looking at functionality. Can you debug it? Can you reason about how it works beyond documentation? What if there isn't documentation? And can you adapt some of these like techniques and way of thinking to something brand new, right? If you continue down this road, particularly if you go into the CTF scene, you're going to see all sorts of cool permutations of these concepts just reappear in different settings. And that's not only true for the wider CTF scene, but even for challenges that are on the dojo itself. So like one that I think was super cool, that is a community dojo that we were talking about before I started the official stream, is by one of the first community dojo makers, the Hydra Dojo, which was made by Zishan1234. They made a little community dojo that was a kind of disparate set, a bunch of like disparate concepts. Right? So this was like a House of Spirit, some type of ROP thing. This was a SIG ROP, which I've talked about in various streams, but I still don't think they have a challenge on it. And they just got mad. They're like, you're talking about SIG ROP, but there is no SIG ROP challenge. And so they made one. But the challenge that I was particularly talking about was this baby CSU, which is a very cool kind of ROP gadget-y challenge. If you click on it, there's not pre-recorded video, it's not educational, but it talks about this ret to CSU technique. And hopefully, having gone through this course as is, you could take this term, run with it, and solve this challenge. Right? You have all of the kind of underlying techniques and thinking. And so you should be able to look at something that is foreign and not be scared of it, right? Know that you can march in that direction and you'll figure it out, right? And at this point, you probably really enjoy it because you've learned to love Type 2 fun. Twitch says the streams will be missed. So I didn't put this on a slide because I don't want to commit to it. But I think I might try and do some type of YOLO office hours for the wider Discord outside of the structured class as a stream over the summer. We'll see how that goes. So this is not the end all be all. You guys rock and you're awesome. So demo plans. Someone on this Discord and someone in this class on stream said that this module is easy, which, okay.
Whoa.
So you're gonna.
I would not say that.
I said it's easy, right? We're gonna stumble our way around a bit here, in kind of classic Robert style here. I have an understanding of the concepts and how things work. I do not have a canned demo, and we're going to make a do.py and see if we can wrap our hands around this. Somebody here says a summer streams would be goated. I think I'm too old to say that. I think at this point I need to stop saying the cool guy words. But yeah, let's see what we can do. Now, last stream or last week, I said levels 1 through I think 5. Yeah. 1 through 5 all give you this kernel module, and you have quite a bit of control over what's going on, and you're functioning in a dedicated cache for these k-heap objects. 6, 7, and 8 is where it starts to get fun. So 6 is what we will use as an example to poke at.
My pwn.college just goes.
Your pwn.college froze? Perfect. Is it bad?
Yes.
All right. So it's one of the downsides of, I don't know what I had in those terminals. One of the downsides of my evening schedule here is it's also when people decide to get on and start working on things, and so I get cursed a bit there. As somebody found out a little bit earlier, I thought I fixed some GDB stuff, but I still broke some GDB stuff. But you can kind of get around it. I don't know. It kind of works. I dream of a world where it just consistently works. All right. So the kernel challenges, as you know, have to run inside the VM. So I did VM start. We'll do a VM connect. And the VM here is blazingly fast. If we take a look at what's in challenge, it shouldn't be a surprise. There is a version of Linux kernel and then a kernel module. So let's take a look at the kernel module here. I need to send this to. Okay. So what do we want to look at? Like we're looking at this kernel module. What do I care about?
Maybe.
Init. Okay. So you probably noticed that. What was the vernacular or terminology we used in kernel security for these things? It's like init mod or something like that. Mod init. Like the thing that I'm just pointing out is that the name of the actual functions that are called at, for instance, module load or module open, do not need to be whatever we used in not this module, but the kernel security module. That is the kind of default that we use in kernel security. But when we look at this module, it's not called like mod open. I don't remember what the default is. Instead, these begin with kheap, and we have these wrapper functions. These are what's actually called when the module is initialized. And so that is calling the underlying kheap init. So at load, what do we get? It's easy. The flag's already here, right? So we're going to open the flag. We are going to zero out some region of memory that is aptly named the flag. We're going to read from that file into the flag buffer and close the file. We're then going to register a
Kernel.
what do I think of? Character kernel device. That is named kheap over here at proc. All right, where is flag?
Somewhere in
It's
basis.
it's somewhere. Okay. The other thing we might be interested in is what happens at open, right? So when we open this kernel device, these do call kmalloc trace. The trace part is honestly kind of a meme for our purposes. Kmalloc trace is essentially kmalloc. So when we open here, what's happening? We're going to print something. What do we print? Kheap device open. Oh, that's pretty useful. So where does this create a allocation object?
Where's the allocation?
Yeah.
Where's the allocation?
So this is what's different from like the first 5, if I remember right. The first 5 at init, I believe it was at init, they call kmem cache create, right? And they create a dedicated cache for your kernel objects. Does this go to a dedicated cache?
Well, it's some sort of dedicated cache. It's for user input stuff. The GC, the kmalloc GC version. But I'm blanking on the terminology.
All right.
But
So it does interact with some cache.
Yeah.
I agree. But we're not specifically specifying I want to go to a dedicated private cache,
No.
right? We're messing around with one of those community general caches. All right. Pro tip for working on these. Do your edits outside of the VM. Do your compiling outside of the VM. Run your exploits inside of the VM. Okay. I know I need some ioctls, so let's include sys ioctl.h, got a void main. Obviously, you've been doing the first 5, so you have some nice, clean function template, and I'm going to write some utter garbage. Don't copy my garbage. What do I want to do first here? All right, I want to open the kernel device. I need to interact with it. So let's call open, which is also going to have, somebody says, are we going to make the kernel panic today? Absolutely. There is a very high probability of that occurring. I would be amazed if we get halfway to where I'd like to get today. So I want to open this kernel device, which is at proc kheap. How do I want to open it?
read right.
Read right? Is that how I do her? I'm just going to be forever broken from my Windows experience. I'm still reading on my own time now, like Windows stuff. I've gone down the rabbit hole. So I'm just going to be functionally broken for some time. Hopefully good things come from it. Okay. So I can open this, and that is going to cause this to occur. You agree? Now, we don't know what cache is being messed around with. We could look at these args and deduce that this is probably not a size for an allocation, because I have to specify a size. I would, maybe this, maybe not. I don't know. It turns out if you try and look up the args to kmalloc trace, you're in for a bad time.
Very balanced.
So kernel documentation exists as for a lot of the functions. They are similar to man pages. You can't just man them. But if you Google them, you'll get man page like documentation. The kernel documentation is much more fluid, I would say, and a lot more figure it out. So maybe that's a size, maybe that's not. How could I figure this out?
We have a working theory that this is a community cache. So
Okay.
I would like to just look at the community caches in the /prog/lab info, and then see which one gets increased. Well, I'd like open a bunch of FTs and see which one gets increased a lot more than the others. That's probably the cache retroactive.
All right, that's a very I've trained you well. That's a very Robert way of figuring things out, right? It's just like, I don't know, man. Let's just poke at it and see what changes, right? I know what I can look at. Documentation is great, but let's make 100. I don't care. Let's run something and just see what we can break or what we can change. Is there something I got to include for that? Yes. All right. So hopefully nothing is going to make 100 allocations happen. I'm doing something obscene. So let's compile our do.c. Let's run our a.out here. What's that?
We combine.
I compiled outside. Maybe 100 was too many.
Maybe check the envelope.
Maybe. But I've been in this field long enough to be an optimist. All right. I want to believe. You want VM logs? We're opening things. Okay.
Stuck.
What are we stuck on?
Oh, good job.
Working as intended. Well, why do I need that get card?
Well, we want to check the slab info before it gets released.
Right. So if I didn't block here, then my program is going to end. And if my program ends, what gets called over here? The release function, which is going to free an allocation. Was that the same pointer? I didn't verify that. When we open, we set this to be v2. If v2, yes, v2 is the private data. So if we succeeded, we do some nonsense here where we zero it out, and then we put that pointer to get the private data. And so on kheap release here, we are freeing that same pointer. And so if I were to exit my program, we would let go of all of those right away, which would become a problem. So let's VM connect over here. Look at the old slab info. Okay. So this should be one of these, we believe, one of these kmalloc CGs. And the reason for that is the kmalloc and kmalloc CGs are generically sized caches. The CGs are for objects that do contain userland data. And we didn't see it yet in this module, but we do have the ability to write. So let's see if I can get these side by side. Kmalloc, CG, bam. I'm just going to use the power of GD or of Tmux. So before, bam. After, now CG. Bam. Okay. Did one of these go up? Oh, let's grab our headers too. So that way this is all pretty. Oh, look at that. Oh. Yeah. I think it looks good. So which field do I care about? I got this slightly not right, if I remember right. Last week. Is it the active objects? Did one of them go up by about 100? Okay, so this was at 32. I allocated 100. It's not exactly 100 because remember, other things going on can utilize these caches. Did any of the other ones go up by 100 by chance? Am I just like shorting out early here?
What the by 500?
Which one?
It's CG64.
CG64 went up by 500. Okay. So it could be CG64. Everything else looks about the same. I'm a believer in 512. You a believer in 512? All right. Do we? And I don't know that this is true. Like, I just make stuff up as I go here. Right. Does that coincide with our thought here? That this might be a size. I don't know that it is. But if this was a size, would it be in the 512 cache?
Yeah. Looks like it could.
Yeah, maybe, maybe not. No, but like, this is what I mean when I like you can laugh a bit about it, but legitimately, if we were to go here and look for what was it? Kmalloc trace. Show me Kmalloc trace kernel. I get Kmalloc. Okay, so that's silly. Let's quote this, right? I'm going to trust the Googs.
That's a random Kmalloc.
This tells me that there's Kmalloc. This is like some Stack Overflow, right?
This is talking about random Kmalloc.
Random Kmalloc caches. This is, where's my man page, man? Oh, okay. We have something random from Google. Anyone have a better approach? I have one thing I'd try. Is it just, it's all over now? Google doesn't have it? We live in the future. We could ask some AI thing, but I still don't trust them. We could also go and look for that in the source, right? What was it? Kmalloc trace? I don't know. Rip. Kmalloc. Did I misspell something? No. Is this some weird kernel thing where there's no? So we're just.
So
Okay. Uh, is it all over? Maybe. So what do you do? Does this just mean we give up and we can't move any further? This challenge is unsolvable? And I can get K Malik. Do you, by chance, Twitch, know if there is like a dunder for this? Like, is it a macro or something that I'm... Twitch delay, the Twitch delay is real. But yeah, so we're kind of SOL here as far as trying to contextualize what's going on. So my kind of nooblet idea here that, hey, this is a reasonable number to be a size isn't a horrific idea. Doesn't mean that it is. Because we're also specifying a cache right here. So maybe this cache is specifying the
I think
size.
you can check out. Might see better.
You wanna
Size. Since,
what do you want to do?
well, I know that K bioptical does some allocations. So like it has a option to allocate a couple objects.
I want to know what is going on right here.
Right.
Right? Nobody knows. Twitch says, yeah, they can't remember the name. So you know what? Our kind of gut vibe check is totally fine.
Well, we could.
We could GDB it, but is GDB going to...
It takes some time.
Well, what are we going to GDB it? Like, I'm happy to just explore here because my biggest goal here is to not have the flag fall out on stream, right? I think it's far enough removed. Okay, someone is saying that they think they found it.
Yeah.
Let's see. They're on slab.h, which I think I can get to from here. And they're on line 525. My slab.h.
What's the different budget?
Oh,
They're at 6.7 there.
I'm just curious now. Is that okay?
Yeah, it should have.
Okay. It helps if you're looking at the same code. But look, my gut check.
That's correct.
It's a size. I don't necessarily know that it is the size of the allocation, but it is in fact the size. Thank you for that, Twitch. And kind of getting that intuition or having that intuition, whether it's right or wrong, I still would have been happy with it, right? Is that meta skill that I'm talking about here. It looks like we can look at the implementation. Where is this size used? Of course, Kmalik trace calls trace Kmalik. Who could have thought? But this is really what we're after. 194, 265. I want to go down the rabbit hole now. Just another day in the kernel. Size. Object size from develop controls. Okay, it's definitely using the size value for the size of the object. I am happy with that.
I'm happy to.
I think you're just like, this is a clown show. But it's a fun clown show. Twitch says you're as reliable as AI. You're more reliable than AI. Okay. So I can open this thing. We know we're interacting with the 512 cache. As was kind of pointed out a little bit ago here, what is going on in this IOPTL thing? This is a kernel module, so we can open it, which does something. There is also the IOPTL, which is how we're going to communicate with this thing. Now, this exists in a little bit easier form in some of the earlier challenges, where there is some constant that is a command based on the command number that you are passing, we will perform some action. So it looks like we, oh, I have some idea of what this is already. That's why it's no fun. What are we interacting with this thing? So when I perform the ioctl, I give it arbitrary command and in this pointer to a buffer, right? How is this being used? Well, the command is being checked. All right, that's a no-brainer. But what is going on with this buffer? Because we have this request thing. What is the request thing? It's the buffer that we passed. It's being, so whatever we pass as an argument is getting copied into, or copied from the user into kernel memory at this request address. And so we need to make sure that whatever we pass as an argument here is structured as this request struct. Do they call it a struct? Oh, it's so nice. They even call it a k-heap request t. So this request guy consists, we said it's what, 16? It's got to be 16 bytes. Hovering this, we see request size is at offset 8. So there is something followed by a size. And if we pass hex 5702, we can't have a size greater than 1D0. If we do, we get a bad result. We have the ability with hex 5703 to free the private data. And we already said that the private data was that thing that was initialized at open, right? Cool. 5704 lets me do what?
K-malloc trace. And copy plan.
All right, we're doing the mysterious k-malloc trace again. But we're going to create an allocation. We'll notice that that's the same and that's the same. So we're interacting with the same general cache there, which is going to be k-malloc CG512. And we're going to copy the flag into that allocation. So we have the ability to get the flag into the cache. And then lastly, at 5701, we can copy from the user to the private data the request ubuff, which is a void star in this request structure. And we're going to copy whatever request size is into the private data. Does everyone have some idea of what this module is allowing you to do, or should we do a quick doodle? Because I know people are at different points in the module, right? Do you understand this request struct thing? Yeah. You do?
Roughly.
Roughly? Like you built it, you got it working? You built it, you got it working? All right.
Yes.
You built it? All right. So we're going to have to start all over again from the beginning, guys. Okay, cool. So if you already understand how this bad boy works, how did you set this up in your C code?
I just made the same struct as.
So you made a struct?
Yeah, called it something, right? KD, right?
Okay.
And it had a char star or a buffer. Let's call it new buff, same as the buffer. And then the size D for size.
All right. Did you make anything else? So we have this char star, which is a pointer to some buffer. We probably would need to point it somewhere, right?
Yeah, you'd make a buffer name and then point it to that.
Oh, you want to put the buffer on the stack? It feels so dirty. Got this big old buffer on my stack. And I write horrible code, man. I like globals. Okay. So I have that. And so that gives me this struct, this something k heap struct, which I also need one of, right? Because this is just a declaration. So struct something k heap. I'm going to call it request because that's a more reasonable name. And so I need to ioctl with a pointer to this request struct. We ioctl with some command, and then we give it the address of request. But prior to doing this, we need to set up the request. And so we'll say request buffer is going to equal actual buffer, and request size equals, I don't know, 16. It's just arbitrary. You just want to prove that they make this thing work. What do I want my command to be? What are we going to trigger here to prove this thing works?
Let's try allocating it.
I want to allocate an object. We allocate an object here with hex 5704. That looks reasonable, right? Doesn't mean it is. Do you agree? You shouldn't. Okay, so we have that. What do? cd.c. Oh no, I did that inside the VM. We're cursed. gcc do.c. What do I want to do to see that we're actually doing this? I want to break right here. How can I do that? I want to see that we're triggering it, right? I could look again at proc slab info and see if something changed. But I want to set a breakpoint here. What do I want to do?
You go in the VM, sudo cat proc alsins, and then grab from challenge, and then you should see an ioctl kernel column. If you like the address of the ioctl function.
Okay. We're looking for kheap ioctl. I'm over here. I'm broken, man. I'm thinking of CDB. I'm not in GDB. Dude. Somebody says, back when they did this module, they weren't a struct master, so they just kept making uint64t arrays. It works, man. You could, I think when I first did this, I just did a char star buffer and then just recast the pointers to be whatever I needed. Because like, we don't really have the issue here with this struct. But you don't have a guarantee that these are right next to each other, even as a struct like this in memory. The memory layout may not necessarily match what you were thinking in your head, because the compiler may not make this packed. It may try and align things by, for instance, 4 bytes or 8 bytes. In this case, this is 8 bytes, so it's going to work. But imagine that this, instead of being a char star, was like a 5 byte character array. The compiler is not necessarily going to smash the size up against 5 bytes because it's going to try and make things aligned and can add padding as an optimization. And so the most accurate thing you can do is just have an arbitrary buffer and then cast your pointers. But we don't have that problem right here. Okay. Oh, yes. Okay. I am just broken. I don't know how to use GDB anymore. Okay, that is a problem. Set disassembly flavor Intel. Well, that is not super useful.
We find the offset where the alloc is an item.
Okay. You want the offset in IDA. Where am I?
I would look at the disassembly. Yeah. So F0.
Where are you pulling F0 from? From this right here?
Yeah.
Okay.
36.
Okay, so it's also hiding down here. Those IDA tricks, man. You want to break at this plus E0. Yeah?
No.
No?
Well, if you wanted to do the offset is there in the disassembly. I think it's not a different number. So it's plus 90, yeah. Okay, my output plus 90.
Okay. So let's I really forgot how to use GDB. This is breaking my brain.
I think D one
Isn't it disable breakpoint one?
L1 is
that is D.
DL or D. It's still there.
Okay,
L1
so no, I disabled it. I did what I wanted. Okay. CDB is the new king. Yeah, unfortunately. That's what I get for practicing that. Okay, so you want to break here plus decimal 90. Okay. Set it free. Oh, let's make this be something more reasonable. Okay. That didn't seem like that worked. Okay.
Well, I usually just overwrite the 60 and put the F0, which is the offset. Looking for
You overwrite the 60 and put F0?
Yeah.
Oh, because of this right here?
Yeah.
That could be a hex. I want to make it work. Let's pretend that it's hex.
Yeah, that's
All right, so it was hex. Okay. So what happened? I'm expecting to be a call instruction. Where am I on? Okay. So the other breakpoint hit. Okay. So we did hit or it came out trace. So we are able to do that. All right. So our octal works. You agree? Sweet. All right. What is our plan of attack? We've managed to like interact with this thing and we have some basics. How do I get the flag, right? I can interact with this kernel module, I can ioctal, I can create allocations.
I can free out.
So I can create allocations by opening the kernel module. I can put flag in allocations with this ioctal call. I can free allocations by using that hierarchical call. This becomes the ideas and concepts behind the exploit, the beautiful ass of the horse, right? What is our thought process here? Does it involve slots and objects and caches and heaps and these things?
Right now, we could maybe try and print the flag.
You just want to print the flag?
Well, it's already in allocation.
Did I get it in memory? Okay. Yeah, it is still in memory. Okay. Do I have? Yeah, libslub. Oh no. Source opt libslub. Libslub down. Hi. So yeah, if you get an error that looks anything like this, this is because the kernel has KASLR in it. And libslub just says, hey, I know I need to figure out what version of the kernel you're running. And it has a hard-coded address that it looks at to try and determine what version of the kernel do you have. And if we have KASLR, is this hard-coded address going to work? No, it's not. So it's all over. We can't use libslub. Right? That is actually what I told people. I want to say last semester. That's why when I said that we used raw GDB pointers and degraphic stuff, that's what we did last semester. But we won't do that this semester. So we'll VM stop as long as you're in practice mode. If you take a look at, and this is like an implementation detail. You'll see that there are these hidden dot files in the challenge directory. These are what we're setting to configure VM at start. If we don't want the ASLR, we can just remove this file. Let the VM back up again. Somebody says, it looks like we still have a use after free. So that's good as far as thinking about primitives, because I have the ability to free the allocation here. And this is freeing the private data. What makes this use after free? Someone that's not you.
Because it's not zeroing out the data.
Right, we're zeroing out the pointer that's located there. Right? So that means when we do this copy from user, from the buffer that's pointed to by the request struct into the private data, we can use this pointer or this address after it's been freed. And so that's good as far as identifying, what is the primitive, what is the vulnerability, where is the mistake in the code. All right, let's VM debug again. Let's continue it here. Let's see if we can just snag KL Sims grep challenge, you say? We're doing CSE598. And you wanted to break here plus x90. We'll run our a.out. Let's source Jeff. All right, we're at that call. The reason I want to start here is the easiest way to get this pointer if this is the pointer that I think we're after, I could just step and then look at the return address, right? And honestly, that's how I did most of these when I first did it. I was like, you know what? I'll just grab the pointer that's returned from the malloc call. And so, oh no, yes. Did I get it?
We're inside Kernel.
Okay. Okay, good. Which one doesn't work? It's next instruction. When you're in the car, I thought I hit the bad one.
That works. And I sometimes puts you in some weird places.
Yeah, NI is cursed inside the kernel, if you'll recall. But you can SI, you can finish. The optimal strategy, in my opinion, is just to set a breakpoint at the exact spot you want and just don't step. Just set more breakpoints. We look at REX, that is my value, right? So then this is the called the string copy. So let's follow my own advice and break on the other side of this. And then we can examine the string that was at $3, and we see that the flag is in fact there. Yay, kernel heap. Now, is that a good way to think about the layout of the memory of the kernel? Probably not. You want to think about, we thought about, I didn't like this, slots and objects, and like we had all this fancy terminology. And I'm just like, there's a pointer, right? How else may I want to look at this memory location or contextualize what I'm looking at?
Where it is in the slab.
Where it is in the slab. Do you have? I have how I would think about this, but I wasn't doing this earlier this week. Do you have a way of thinking about the way this is laid out in the slab?
Like
I've got
visualization.
yeah, I've got this. What do I want to do? What if I want to think about this in terms of like objects that are near it? I want to think about these slabs. I want to see a slab, right? So there are, I believe it's SV object. Followed by the pointer. What is it? I'm like pretty sure what I want was object from libslab. It still isn't what I'd use because I'm trying to teach you guys the more correct way than what I do. It's not SB cache, it's the one after. It is SB object.
Oh, you didn't source libslab.
Is it? Oh, okay.
I have to sit there.
Yeah, okay. No, I know what I did. I didn't sudo this. So there's a trap right now. I'll just show you my GDB init and we'll hand wave this away for the moment. We'll blow away all the stuff that isn't relevant. Okay. So this is like a Dojo specific thing. If you had a sane Linux environment, you'd have one Python, and this will be the Python that your GDB works against, et cetera, et cetera. The Dojo is a magical place where those things aren't true. And so the requirements for libslub are located in the module directory for Python 3.8. But the GDB that I currently have you on, which I did, this is my bad, is a newer version of GDB with a newer version of Python so that Jeff works. So now you're on the newer GDB with the newer Python, but you have to tell it that, hey, there's modules in the old Python directory that you need for libslub to work. The shorthand is just put this in there for now, if this is still broken when you see this recorded. Hopefully it is fixed. But I have to learn next. That is what is necessary to make this work. I have to cave. Okay. Sudo VM debug. libslub wouldn't have worked anyways. Because you need the root when you do VM debug with libslub. I don't suppose I still have that pointer. So I do. Bam. Okay, so that exists. The command I was hoping to use was resource. A couple things now. Give me Jeff. Give me libslub. I do, in fact, occasionally remember the right thing. It was SB object, but I wanted it to give me the nice, pretty printout. And so I needed a context, give me a context of up to 4 objects, and give me the full print of it, which I think is dash. Oops. There we go. So that, why does that not look like? Oh, it went ahead. Okay. There it is. And so here is our object. It should be 512 bytes. And then the next object is going to be somewhere after that. So we can visualize this bad boy. Where is the object that's after this if I didn't want to rely on libslub?
Right after it in memory,
Yeah, but where like I want to print the beginning of it.
just plus X to 1.
Plus hex.
To 1.
Okay.
That's 112 bytes. Yeah.
So that's at C00, which is what we did not see. So I could have examined, I don't know.
Without the 200, right? Because you want to see the next one.
I want examined 512 hex. Right. So that's the beginning of the next chunk in memory, right? Because all of the, or not chunk, bad object. It's the next slot, which may or may not contain an object. I actually don't know, right? If it contains an object or not. Now, where is, without libslub, where is the beginning of this slab? I know that. Why?
No freaking.
So I can't. If we make a very reasonable assumption about what a slab is, or how big a slab is, can I make an assumption about where the beginning of the slab is?
Well, we know for our purposes right now, our slab holds objects or slots of size 512 bytes. And the slab is usually a page. So it can hold.
It's not usually a page?
It's usually a page.
It's usually a page.
So it can hold 8 objects. Assuming that the first thing we allocate, how many do we allocate that? Like, I think we allocated 10 at that point, so we're the next page, maybe like.
All I'm asking is, without using libslub, where do I think, where is the beginning of the, where's a reasonable guess, because I don't know this is true. Okay. Where's a reasonable guess for the beginning of the working slab?
200 hex before.
200 hex before this.
Yeah.
So you are relying on the fact that I have, I don't think it's true. Why do you say that?
Just the case.
Okay. X 200 512, right?
Yeah.
So you're saying that this is the first object on a slab.
So,
Okay. I am assuming that it is not. And that is because we're assuming that a slab is the same as a page. How big is a page? X 1000. So if I just were to not count this A, I would get to the beginning of the page, right?
Yeah.
Which should be, if we make this leap, should be the beginning of the slab. So my claim is that this is our beginning of the working slab, or at least the slab that this object belongs to. How do I use libslub? I think it's -n. It is -n. To confirm that. Kmalloc CG, we said we're working on 512. Did I guess correctly?
so, yeah.
Where's my working slab? So this is the cache. The free list is this, but that doesn't mean that that is the slab.
Slabby web page ads. Yeah.
Okay, right here. So this is the region that we're working with. This free list is telling me what was the most recently freed object from that slab, right? It happens to be the first object of the slab. It's not guaranteed to be that, right? In fact, if we were to restart the VM, there's very good odds that it would not do that. Any idea why I say that? Is the order of the free list, like is the order of how slots are used deterministic? It isn't on this challenge. One of the things we talked about last week, or at least touched on, was the free list randomization. I can tell you that by you get to this level, the free list is randomized at start. And so what that means is that unless this has been an abundance of allocations and trees, and even then, I don't think we would end up in the exact same state. The order of the free list is not going to be consistent across these. So we have a concept of the free list. We have an idea of where's the beginning of the page or the spline, right? It is this region. And we know that there's 8 elements. Three are being used, and there's 5 in the free list. Okay. And the flag somewhere in here. See if I can make the flag pop out again for good measure. All right. The flag is on this page, which is a slab that contains 8 slots, and there's 5 free ones here. Remember the command to dump out the free list on this? SB cache. Show free list. And probably wants, oh no. Yeah, show free list. Partial. You are not happy.
It's a typo. Trees.
Okay. Why are you not happy? SB cache, partial slab, show free list. Are you going to make me do this? See, these fancy tools. I don't trust them. What would I do? How would I see all the things in the free list? What do I know about how the free list is structured?
That's random.
So the free list at kernel init is random. This free list has 5 elements in it, right? And this is the head of the free list. The free list is a singly linked list, except the next pointer is located right in the middle. But this is 512 bytes, and so if magic tools don't work, I could examine the giant hex that is at this plus 256.
It's hard. It's paper.
So we got problems now. Okay, so maybe there's a reason the magic tool didn't work. I don't know if libslub plays nice with hardened or not.
Well, if you prefer it to eco, at least another and pointer ahead of time. So
Okay, so we got problems. We don't even have a plan of attack though. What is our plan of attack? We have all these problems. There's lots going on here. What do I want to do? The flag is here. We have a flag. If you can tell me a plan of attack, we can take a break. Then we'll come back and try and implement it. Here is a flag. I have a use after free.
well, we know the free list is randomized, so we can't. And we also have a bound of how much we can read.
I have a bound on how much I can read.
Yeah, we can read only up to hex 1d0, which is that means that if we do somehow get the flag right after our kernel device driver, we can't read beyond it to actually see the flag. So we need to somehow get an allocation there which bypasses the size so we can read more and be able to read the flag.
Okay. So we've got this bad boy, which is our slab. We have the flags chilling in some home trunk. We want to read further than what we're allowed to. So I want to be able to get this slot, and I want to own this slot that's before the flag.
Not only that, but also have it read more than what we can read, right?
Okay. So I want to own this slot, and I need to solve this problem of reading beyond. Because if we look at how the kernel module works on its own here, when we copy to user, do we have copy to user? I have copy from user. Do I have copy to user?
Yes, the one.
Okay. So our worry about having this kernel thing that doesn't let us read too far was misplaced because we just don't have the ability to read. So we can write some stuff here up to a point, right? But that's it. But ultimately, I want to read, right? I want to get the flag out of there. And so we have the right idea here where from a heap exploitation standpoint, it would be super cool if I could allocate something before and I could get this to read beyond its slot, right? So like the plan of attack is good. The problem here and why this challenge is like the first of the harder ones is we have to start thinking outside of the kernel module. Somebody says, shit. It turns out there's a reason we have the slides that say like message and pipe buff and these other weird things, right? Because now the kernel module doesn't even provide us the ability to read, so we need to create our own. We'll take a quick 5-minute break here, and we will try and create that primitive on our cache here. So I'll be back in a few minutes. All right, bring you back. I don't know if you can see it or not. Boom, we had a nice discussion where I drew more pretty pictures. Because showing up to class should mean something. Okay, so, also, I found, I'm not going to pretend that I remembered them because I did not. I looked them up because I was trying to show two things using libslub. The first was I want to dump out all of the objects on the page, which should be this right here. And so on this slab, we said there are 8 objects, and F is free, M would be malloc, and so we can see what is the state of the 8 objects that are on the slab. Now, if I wanted to look at the bytes, because I'm doing some type of crazy overflow, we can pass the -x. This is what I was hoping to print out earlier, but I don't know why. I goofed it up. And now what we can see is we can get, this is the beginning of the first object. We can see all of, on the page, we can see all of the byte values here. Here's the next one. We also see whether it's free or allocated. And we will see, here is the one that happens to have the flag. And so when we draw things, which don't show up well for Twitch, but several places now, I've drawn like a slot representation of the slots on the page. This is the kind of GDB equivalent to visualize and see these things, right? Because it's showing me these slots in order in memory, and I can see those bytes. And so for this particular level, where we left off, was we want to try and print this flag. The problem is that this kernel module doesn't even have the ability to print an object. So we have to create that ability. Now, one of the other things that's different in this level than the earlier ones is we are using one of these general caches, right? We are in kmalloc CG512. And that means that other objects than these kheap objects can end up in this cache. For the first five levels, it is only kheap objects that are in the cache. So you can reason about the structure of everything that's in there, that everything is homogeneous, right? They're all the same object. But in this level, we don't have that. And so what I really want to be able to do, because the flag is here, I can make a kheap object, but a kheap object doesn't let me read. I want to create an object here that allows me to read. Based upon the slides from last week, what is an object that might be useful in this regard? Now you can speak. Yeah, you're allowed to speak now. Message. Which is why we spent a little bit of time there. Before I set GDB free here, the other thing that I tried to do that I goofed was dumping out the free list. My mistake here, this one I do know what I did, is I did show free list instead of show lockless free list. What we want for everything we're doing is show the lockless free list. And so when I do SB cache and kmalloc CG 512, then it says, hey, the free list begins here, right? And it has 5 elements. These are the 5 elements. And so we don't necessarily have to go through the Robert way of just like finding what I want using raw GDB, right? If we spend the time to read the docs, somebody made a nice tool to just print this. Okay, so how do I get a message in here? I said in last week's lecture that the way that we create objects, or not that we really don't have the ability to like create an object name, right? Well, we can encourage the kernel to create an object. And in many of these cases, it's just required for the kernel to do its job. It has to create an object by performing specific syscalls. For message, do I by chance still have my demo code? Or is that the do.py that I removed? Oh no, I hid it away in here. If you'll recall, this is how we use message. We create a message queue with message get, and then we can use message send and message receive to read those messages from the message queue, right? So as part of creating a message queue, the kernel has to allocate an object of some kind, right? There must be some internal representation of this queue. Similarly, there must be some internal representation of the actual message itself. I don't care about the queue for our purposes, so we're just going to kind of yoink this right here. I guess I need to yoink it a different way. We are going to ram that into our do.py. Maybe. I really want this to line up. Whatever. It's at the beginning. Gosh dang it. Okay. So we'll talk through it as I fix the indentation. What cache size are we targeting? 512. I need to have a message buffer because that's going to be how we set the values of this thing. I don't care about this. This is part of the demo. If you recall, the way that these messages are built inside of the kernel is there's really a struct that is just a header that has some metadata, and then the bytes that immediately follow that header data is the message itself, is the message contents. And so what I've defined here, this is missing, okay, no, there's the is how I am going to treat my message, which is going to have 100 bytes. Do I want 100 bytes? No. I need this to be bigger. Doesn't really matter, because this right here is my userland representation of the message file, right? Where I'm actually constructing the message in the kernel. Oh, I did mess it, whatever. Is when we message send, right? The message send is going to grab from the message buffer to create a message object of message size. But this message size that I'm specifying in the syscall does not necessarily, if I were writing perfectly correct code, this value should match the size of this struct. It's not necessary, because what this will do is it will copy these bytes, or it will start copying from the beginning of the struct. Technically, it's this location, it's on the stack. It would copy from the beginning of the struct, and it would just copy message size bytes from the beginning. Right? So I can make this larger than the size that I actually am copying from userland to the kernel. Does that pass a sanity check?
I want to be more than this.
I was on. I need another 0. Okay. So I have that. let's start something simple here. So I am creating one queue, and I am iterating once, despite this being in a for loop. Hopefully I got that correct. Let's double check real quick in a QID, pointer to the message, message size, and then flags. Okay, so I would have blown up. That should be a valid call. I don't care about that print. This is what I want to do. Okay. So our state was, as we saw here, some things are malloc, some things are free. And the flag is somewhere in one of these slots. My goal, assuming I cobbled this together well, I'm going to perform the same steps here as what I did earlier, except I'm going to send a message. And this message should be of such a size, which I took my target cache minus x30. Is how I'm getting this size. The reason I'm saying minus hex 30 is because that is the size of the header data of the kernel representation. Okay. This is my userland representation of my message. But the kernel, if we go back here and we find, what is it? Is it message? You'll see that the message struct inside the kernel has metadata for the kernel to manage this internally. And then it says the actual message, so what we think of as the userland message, is just appended to this struct. And so the hex 30 should be the correct size to account for this. Because what I'm trying to do is make the kernel allocate a message internally that is going to end up in the kmalloc CG512 cache. And so that means I need to strategically set the size so that this message will end up in that cache. That's where the math is coming from. Now, to hopefully show that I'm really doing this, let's set, what do I want? It's mem set. Message buff, message. Let's set, I don't care, 300 to be the character A. All I'm doing here is I'm ensuring that the message buffer of my message buffer struct inside userland has a bunch of A's in it. So when this gets copied into the kernel, if I did this correct, I should be able to run that same SB object here to dump out the objects on the page. And I should see one of these has some A's in it. Doesn't mean it's going to work, but that's the theory. Cool. GCC or do.c. It's mad because I need to do some includes. I have sys types. I need sys IPC sys message. All right. So let's run this again. Did I also yoink some nonsense that I don't need? Whatever. We can mash enter. I should be at this next get char. And now I've done it twice, so we'll see what happens. Sudo vm debug. Let's run our SB object. Is that still? We'll learn together. I wanted to SB object C8 X page.
Is that gonna be the same in this one?
So you're saying, is this going to be the same page?
Like, is this gonna be the same slab? Like, did we just allocate to that slab now? Then when we reran code?
So I'm making an assumption that between my first run and the second run, because remember when the program ends, I'm releasing everything. So whatever I was doing on the slab is no longer allocated. And then I do the exact same series of actions. I'm guessing that I'm going to end up on the same slab. Still can't type, but I can guess. Oh, I didn't specify a slab. That's going to be cursed. -n, kmalic cg 512. Why are you going to page this? That's silly. Okay. I still have the pwn.college. I don't see my A's. Let's SB cache, kmalic, cg 12. Real 3. C8 real 3. Oh, well, you're right that the message queue would outlive me. Because the message queue lives beyond the scope of the current running program. And so in that sense, you're true. All right, let's restart the VM. I want to believe. Because one of the problems here is that what happens when a slab is filled? Do I have a reference to it anywhere? No. And so I don't know if I'm doing my message wrong, or if I'm just not looking at the correct page. Okay, let's look at SB cache for kmalic CG12. Okay. And then let's SB object this thing. I want to look at 8. The memory and look at the beginning of the page. That is the beginning of the page. Yeah. Kmalloc, CG512. All right. So we see there's now some interesting stuff in here. Because again, we're in a general purpose cache, right? Okay, let's fire off here in the VM. Let's just look again before. Gosh dang it. Gosh dang it. It is a different page. So things are happening on the kernel. Okay, does that coincide with my interpretation of reality here?
Well, we're before reading.
I'm before the message get, but am I before my ioctl?
Yes.
Okay, so I wouldn't expect anything there. Now I should be past the ioctl. Was there more nonsense happening on the kernel? EF6, 8, objects, 8 in use. Okay. Previous has 6. Oh, that's just the object. Cache. Okay, there's 6 things on the free list. It could have been on the other chunk. And this is our kind of challenge when we, well, let's not quit, let's just continue. When we talk about trying to create a scenario that is conducive to this, right? Because we saw, I tried to do this several times, and I'm not even on the right page, right? And so we want to try and spam across this to create a higher likelihood of the scenario being in our favor. How can we do that? We'll go back to like it's silly, but it's just like, yeah, let's put a whole bunch of flags on it. Right now I'm not even seeing the flag, right? So let's see if we can sanity check our way back to at least where we were. So we'll compile it. I'm already in the VM. What are you doing?
Well, you're not putting any flags by calling open key.
Oh, you're right. That is allocating the nothing burger.
Once you're out before the message maybe.
So I want,
Could have a bunch of IOPTA calls before the stop before reading, and then check the flag there, and then see what it looks like after the message. And
correct me if I'm wrong. So when I open the Kmalloc is called.
Yeah.
Okay. When I do the ioctl, I
You stir
I'm
copy.
doing the stir copy.
Yeah.
So if I wanted to fill it with flags,
You want IOP.
I want to open and ioctal.
Well, you can do only one open, but you can IOP a bunch.
Why can I only do one?
Well, you could just do one. You could do multiple opens, but then you're filling up pages full of nothing.
Oh, because this is doing.
Because only the IOP will put the flag into the actual object family, the content of the object.
Okay.
The open just opens a bunch of
The open is allocating a nothing. This just the ioctal is putting the flag.
Yeah.
It's doing its own k-malloc for the flag. It's not using the malloc from the open. That makes sense. Well, let's follow your advice. Somehow, while I was doing this, I blew away my ioctal. Yeah.
gone.
Okay. So after, I can't imagine why this is going off the rails.
So you have a curly bracelet. But
Okay. That goes there. I want a ioctal on the file descriptor. I want my command to be 5704. And I want my buff that I'm passing to the ioctal to be the address of request. But this needs to happen after I set up request, which I'm also not doing anymore. Somehow
So,
I blew away that. My refactor was just insane. Okay. So I want request buffer to equal actual buffer. I want request size to be, do I have a limit on this? I don't think it matters. Let's say 200. Do I care about actual buffer? Yes. Let's memset actual buffer to be B's. This way we can, if we see this, we know what it is. Because that will get written somewhere. Okay. Get him, rerun our A dot out. Get here. This guy, I have to tab 7. Show me the beginning of my region. Can I SB object this? Do I get? Okay. I've at least got a flag there. I'm not sure what's going on with my message though.
well, how about we do 8 IOP calls instead of 80? So then we know we are filling up at least one page for sure.
So, okay.
And then we know that at least the next time the kernel will grab a cache, it will be from the next page right after we do that. So instead of doing 80 and then maybe or not, or like however many pages after, like, I don't know if that makes sense.
So there's some sanity to what you're saying. If I do 8, I know I filled a page. It doesn't guarantee me the state of the current page. Right? Because I could have had one free to begin with, and now there's 7 flags on the working page, or there could have been nothing on the original page, and I've now allocated 8 of 8, at which point I'm now on an empty page.
Well, in both cases, I will be on the same. We will be on the same.
You will have at least moved to a new page. I agree. Why does this make sense? There was one allocation before we allocated 8. You're just going to mod yourself because you're going mod 8.
Yeah, but
I'm not saying that like 10 is the correct number or 8's the correct number, but we should be able to, if we're thinking about this, right, get more than one flag on here on the current page. We should at least be able to do this. This has nothing to do with message.
because we might output this.
At the before?
Yeah.
Okay. One, two, three. All right. So
we don't see our message.
We don't see our message, right? Our message stuff may be cursed. We have to sanity check that, but we're at least getting flags on there. You agree there? Okay. Twitch says giving away working code for the last lecture. Yeah, the
Working.
yeah, that's quite the definition there. All right, so let's think. What is off here? I'm sending message.
We already stopped before our message gets sent. So why don't we check the page that we know we're on? Then, but we already don't see our message there, so that's the issue.
String searching for our aids be a viable sanity check here?
So we could do that. The problem with doing a text search, in this case, is that the pages themselves of this lab are arbitrarily they're not next to each other. So we would have to be scanning a really big region of memory to try and find it.
Isn't there supposed to be like a receiver or something? Or is that not necessary?
I'm sorry?
Wasn't there supposed to be like a receiver?
So-
or is that not necessary?
So for the way that you use message, right, is one process sends, and that puts those bytes in the kernel. Okay. The other process receives, which then reads those bytes. It's not directly reading the kernel, but the kernel copies it and gives it to you, right? And then the kernel frees its internal buffer. Right.
Maybe we should allocate more than one message.
So I could allocate more than one message. I don't think that's the issue. I think we're hitting a different cache, is what I think's happening.
Size should
I don't know why I say that, but like It's the only thing that makes sense to me. And I'm not sure entirely why.
Is it because our buffer is hex 1,000, maybe?
So
But that's not where the
this, right, this shouldn't matter because this is just whatever happens to be in memory in my exploit process. Right. So this doesn't matter. What should matter is this size right here that is being passed. Oh, I am really dumb.
You never pointed to them.
No. It's all because I YOLO stuff, man. I copy code and I just trust that like prior me was good. I copied this from the receiving side, not the sending side, which doesn't. I fixed up the one thing so that we're sending instead of receiving, right? But I said that we're making a queue. This isn't making a queue. This is trying to open an existing queue. So right now, if we were to look at this, if we were to like trace this message get is going to fail because there's a specific flag that I'm not oring into this right here. It's like IPC create. I have to check the doc real quick or the man page real quick. But there's a specific flag to create a message queue that I am not doing here. Since this is failing because I'm trying to send down an invalid queue. Therefore, it doesn't malloc anything because you don't have a rate queue, and the kernel's just like, you're stupid. And the kernel is right in this case. So if we look at message get, it is IPC create. Okay. Cache, give me a region of memory, show me some A's. I want to feel like I successfully demoed something. Got some flags. No A's. Okay. Let's trace this outside of the VM.
I want it to fail because we're trying to all create out the business and stuff. So you could comment down the diagram.
I guess I can trace it inside the VM. It's just going to be slow. There's my octals. That's my block.
Oh,
Okay, so I'm still blowing up.
it's not fair.
What am I doing wrong there? M type. Got to be a positive number.
That's just invalid argument.
What's that?
You're saying invalid argument. What the message sent?
Yeah. I see this. Hey, thank you. Thank you for pointing that out. Would you like to provide some other advice? Okay. I believe this is also a failure on my end from that same thing. If we look at message send, what I care about is the struct message type must be greater than 0. Is 0 greater than 0? No, 0 is not greater than 0. I believe that is why it is saying this is an invalid argument. Again, the reason that is 12. 12 is a great number. Build it over here. Let's trace it, sanity check. Okay. Right? It turns out if you pass the correct arguments to the syscall, the syscall will in fact occur. All right. It's poetic that we end up back to read the gosh dang man page. Okay. Did I finally get something in this? Yes, I did. So there was nothing wrong with our high level thought of this. All of my mistakes is because I copied code from my demo earlier, and it probably would have been faster to just write it all by hand, because then I would have thought through what these arguments were. Fantastic lesson. Okay, so now we see that I can use message to put something that I control in here, right? And in theory, I think I did quite a few if we looked at that S trace. I'm doing an abundance of sends here. I probably don't need to do that many because I'm going way off of the current current slab. So let's fix up our code here. How many do we want to send? Or how do we, I guess the better way of putting it is, what is our ideal state, right? I want to have what?
Slab full of flags.
Do I want a slab full of flags or do I want a slab full of messages?
A slab full of messages is just one flag. Okay.
Okay.
And then we can dump a lot from one message and hopefully it will print out the flag.
So if I can get a message buffer behind the flag, that is a good thing. Part of the reason that why it is a good thing is because the size is in that header data of the object, right? So what I want to try and create is a setup of three things. I need control of three slots right next to each other. I don't care. I'm not going to forget. I'm going to forget about the page in Vision. I need a message. I need the flag. And I need something that lets me corrupt the size.
Are we not able to write the messages? No. We're not watching to messages.
So I, from userland, have no pointer to message. Okay. So we've seen how I can get messages in here. We've seen how I can get flags in here. I got to deal with the randomness of nonsense. Okay. I don't care if I solve that problem today. The other piece, because that's just a matter of grooming and allocating, looking at it, and kind of seeing if you get one. The next last kind of piece of the puzzle here is what do I need before the message to corrupt that m_ts of this message struct. So do I have something that allows me to write or overwrite? We said that this kernel module doesn't let me overread, right? Can I overwrite from this thing? I don't know. I'm legitimately asking.
Because I'll check for the size at the very start.
So this is
part of the size here.
copy from user is 5701. You agree?
At the very start.
The size check. Okay, it's ORed, right? So required size if it's greater than 1D0 and 1D0 is less than 200. Okay. So that is a problem. I can't just directly do this. So now I have this problem. How do I create something that lets me do this? You've done this in the earlier levels.
You do have a use of it.
We have a use after free. What can I do with the use after free?
The issue is we can't read.
Do I need to read?
Yes, because the pointers are manual, so we're gonna need to. Actually, I don't need to read. We don't need to read.
Why do you say? Like I'm not, this isn't a rhetorical thing. I'm legitimately like problem solving my way through.
What I'm thinking is, if we have a use after free, we are able to, in the middle of the allocation, or middle of the object or the slot, have a pointer to the next free list object. But that pointer is hardened, so we need to get another pointer that is null. But we can't print out those pointers because we don't have a read. Unless there's another way to.
Okay. So that's it's a good observation, right? From the raw kernel module itself, I don't have a way to read, is what we're claiming. I just want to make sure that's the case.
Say copy to.
Leave copy from user. I don't have copy to user. Okay, we can still do this. So when I use message send, I could write bytes in here. I could then okay. All right, I know what it is. I had to think through it. So if I have a use after free, then the slot is free. You agree?
Yeah.
If I were to put a message in it,
It's not a pointer.
I still have a pointer to it.
Is what I think. Because we can, for example, have we have opened the kernel device driver, move the kernel open. And then if we free that, we should still have pointer. And then if we put a message there instead, we still can overwrite it to the pointer of the thing we opened.
So we can message send to put something in here, right? To allocate something. And I can free something that's a message how?
Oh,
I haven't done it, but we can.
free a message.
Yeah.
Receive.
We can message receive. So I have, I guess I'll just vim it up. I have the following. I have to run through what are our primitives here, like reason our way through here. I can allocate a message with message send. Or is it this? I can free a message with message receive. Are you trolling me, Twitch? So I can do that. I can allocate the flag. What else can I do? Can I free the flag? I can key free private data, but this
Oh, yeah.
isn't private data, right? So I can't free the flag, but I can free
The thing we opened.
the thing we opened, which we can copy from the user.
Yeah.
Okay. So I can allocate something. Some user-defined bytes. And I can also free this user-defined bytes. Is that accurate? Is my copy directly to?
That's
That's not.
the copy from users down.
That's okay. So that's directly to private data, and private data is in fact the beginning of the object. Okay. So if I have a
So we have to use after free. So if we allocate the thing we open, and it's the only thing that's free in the slab, and then get a message thing there, we still have a pointer to that location in memory, and then we can overwrite it. Am
okay.
I wrong in thinking?
No.
So
Okay. So I don't need this.
yeah,
I don't need this thing before, because what you've said, I still need to correct the size.
yeah, which I already have a pointer to the start of it.
So if I have my use after free pointer is to the beginning of this,
I can corrupt the size.
then I can corrupt the size because I have an arbitrary write into this header data. Okay. And by arbitrarily corrupting this header data, I can, while the message is allocated. So the message is in the message queue from our side. We use the use after free to corrupt the size. So then when we message receive, we will read a message, but the kernel will think it's bigger than it is. Okay. It is solved, right? So we have a plan of attack. We've seen the pieces. We didn't have to do anything crazy before. I think it'd be more fun if we did. Because you can end up with scenarios. Similarly, this idea of using message to leak information. If KASLR is enabled, when we think about like pipe buff, for example, which is this other kernel object that we talked about in the slides that isn't relevant for this level. Pipe buff is interesting because it has a pointer to, I believe it's called pipe opt. Pipe buffer. Pipe, that was close. Pipe buff operations. And this is a pointer to a vtable of function pointers. So how does your pipe, get free? How do you read from the pipe? How do you write from the pipe? Right. This is a pointer to a struct that is function pointers. And so this has a number of valuable properties. One, these are function pointers, right? So when you think about indirect calls in corruption, there's interesting things there. If I'm able to corrupt this, then I have essentially what is in level 2. Additionally, if I'm messing around with this pipe buffer, whatever cache has the pipe buffer, as part of allocating and freeing this, it would place pointers that would leak kernel addresses onto the page. Right? Because this is a pointer to another struct that I'm going to guess is dynamically allocated. Right? There's no reason that there would be like a single global pipe op because this is something that's going to be customized. And so we have a pointer here to a page that's backing the pipe buffer. So this is going to give me probably a kernel leak, or not only kernel leak, but a heap leak in the kernel. Okay? And so we may end up having to do a song and dance allocating something like pipe buffer to get addresses into slots that we are interested in that we then leak via this like message mechanism. For the last two levels, the recommended reading is insanely relevant. This one in particular, because you can end up with scenarios. No, that one's okay. Yeah. Where right here, we're just using message, and we have the ability to correct the size. But in this message also has a next pointer. And so you can end up in these scenarios where you end up having to create multiple messages that have next pointers to other regions of the heap to then corrupt things and like create a fake message. Like this type of nonsense is very relevant to the last couple levels. So if you get stopped there, so it's okay, right? There's got to be at least one hard challenge for the blue belt.
One.
Just one. Okay. Everything else I understand was way too easy. We'll try and fix it next year. But this the last two challenges here, hopefully, can give you an appropriate amount of grief. I don't mind giving you a plan of attack here for level 6, because you're playing around with this new concept, right? 7 and 8 take this concept and really run with it. Questions, comments, concerns? Sorry, I fail voted there by copying my own code. But it's probably a useful learning opportunity there. Hello, Twitch. Thank you for popping by. Now, was this useful?
Yeah.
Okay. It's hard to tell. All right. It's hard to tell if I actually conveyed thought or if I just wrote things, wrote code that some poor sap is going to copy and
Have their own mode.
what's that?
Have their own mode.
Yeah. My moments are preserved forever. Okay. If you guys don't have any other questions, somebody says I got stuck there forever. I hope you're talking about 7 and 8. I think you are, if I remember right. Somebody says they hate pipes. And if you go down this, it's funny. I was reading before I came up here. Definitely not while driving. I was perusing Hacker News, and like the second or third hit was actually a write-up. Let's see if it's still there. News Y Combinator. What? Boom. Well, there happened to be a Linux kernel exploitation write-up, what I found quite funny, right? Since that's the topic that we're on. In this case, they weren't using, I didn't finish it because I was focused on other things. But they were focusing on a different structure than what we were talking about, but it utilizes a very similar mechanism because this is how just kernel exploitation as a whole works. This is the only diff that fixed this bug, right? In the kernel. So that 5-line code change. Because it was possible. And say, what did they do?
Got rid of the remove bound function code.
Well, no, they're still removing the.
Oh, they're still removing.
So the problem is that they were removing the bound
When it wasn't dead, maybe?
when it wasn't dead. And so in this case, I made it through a little bit of this. They were doing reference counting, which isn't something in the heap. It isn't something relevant here. Reference counting is a way of tracking how many pointers are there to a dynamic object. It's kind of orthogonal to the implementation of the heap. It's a way of managing memory. And what you do is every time that you create a pointer to that dynamic thing, you increment this count. So the first mallet is a count, and then if I were to duplicate that pointer, we increment it. So now I have 2 pointers to it. You're just keeping track of how many pointers exist to a dynamic region memory. And then every time that pointer leaves scope, right? So if it's a local pointer and it function returns, so it leaves scope, you decrement that counter. And if that counter ever reaches 0, then you know there are no pointers to that dynamic memory. So you know you don't need it, so you can free it on the back end, right? And I did not finish reading it, but my understanding is that they could free it when there were still existing pointers to it, because in their reference counting of the socket, they weren't handling that case right. And just that, right? And I don't know the size of this socket struct that they're using, but as soon as you have that, you have a very similar primitive to what you have right here. And now it's just a matter of, can I message my way to massage the heap and groom it into the state that I need? Can I abuse that one use after free to gain control from? I thought it was kind of uncanny. Super cool stuff. Question: how do people find the useful structures? So some of them have been around forever, which those are the ones that we talk about in this class. If you do some internet sleuthing, you'll find there are many others. Like I have an internal list of handy structs that I'm not going to show on stream. Just from my own perusal and interest, right, reading about how some of this stuff works. And I'm sure there are plenty of structs that I don't know of, but people who spend a lot of time in the kernel do. Giving away, like message is used so often everywhere. Like I'm not giving away some deep secret trick that somebody is using. But if somebody has found a bug in a bug or specific property of a struct that they like, they're probably not going to share it if they're like deep into kernel exploitation, which is one of the kind of catch-22s when you want to talk about this, in a larger educational context. Just like how we talked about, not that we didn't, but like old school libc heap and then safe linking, like things change. And the more well-known, especially when you talk about like kernel exploits, the more well-known specific patterns become, the more likely they are to be changed. Now, some of them can't be changed, at least not easily. Like when you think about message, it's been around forever. How else are you going to implement a dynamic sized message? Like there is a cap for how big a message could be. Like we could hard code everything to be the maximum message size. So I'm going to send a message that's 32 bytes, and we're going to allocate whatever max message size is. But that is quite wasteful in and of itself, right? And so it goes back to trade-offs. Oh yeah, mod probe path was changed. Mod probe path was good at the time of recording. All right. Like the mod probe path is no longer there. Although somebody, I think it was you, said that there is a roundabout way to do mod probe path. I don't know what modern mod probe path looks like. All right, if you guys have nothing else, I am past time. This is the last stream of the semester. I will try and say something if we do a regular stream of some kind over the summer. It's always fun to hang out with you guys. Hopefully this was fun for you. It's always fun for me. I'll leave you there. Goodbye. Good luck. Get your belt. Oh, we will have belting ceremony. Do you know when it is? You should know when it is. Tuesday at 1:30. So I guess there will be another stream. It just won't be educational in nature.
Tuesday 1:30.
Tuesday 1:30 Arizona time. So that is how long people have to earn their belt for glory. If you are at DEF CON, I know a lot of us will be around. Definitely pop by, say hello. Yeah. Goodbye. Good luck. Get your belt.